In September of 1930, a 68-year-old man stood in front of a radio microphone in the city where he was born and told an audience that there is no such thing as an unsolvable problem. 13 years later, he was buried under those words. They were already false when he said them, and the person who had made them false had been sitting in a conference room a few hundred meters away the previous afternoon, saying so out loud to a room that did not react. What he had found does not stop at that broadcast. It reaches into every mathematics department operating today. Every theorem in every journal published this month rests on a single page of axioms that nobody can verify, that nobody will ever be able to verify, and that the people using it have agreed, quietly and without quite saying so, not to think about. Of the two men who went furthest into that problem, one died of starvation in a Prague cell in 1945. The other died of starvation in a Princeton hospital in 1978. All of it traces back to one observation, 2 paragraphs long, at the end of a paper submitted on the 17th of November, 1930. Settle in and stay with me to the end, because what that observation rules out is the possibility of ever knowing whether mathematics is standing on anything at all. If you want these episodes without ads, Meridian Labs on Patreon covers every channel in the group, this one included, and it comes with the full research and source archive behind each episode. Subscribe or join if you have not. Let us start where it started. A 68-year-old man stood in front of a radio microphone in the city where he was born and told an audience that there is no such thing as an unsolvable problem. 13 years later, he was buried under those words. They were already false when he said them, and the person who had made them false had been sitting in a conference room a few hundred meters away the previous afternoon, saying so out loud to a room that did not react. What he had found does not stop at that broadcast. It reaches into every mathematics department operating today. Every theorem in every journal published this month rests on a single page of axioms that nobody can verify, that nobody will ever be able to verify, and that the people using it have agreed, quietly and without quite saying so, not to think about. Of the two men who went furthest into that problem, one died of starvation in a Prague cell in 1945. The other died of starvation in a Princeton hospital in 1978. All of it traces back to one observation, 2 paragraphs long, at the end of a paper submitted on the 17th of November 1930. Settle in and stay with me to the end, because what that observation rules out is the possibility of ever knowing whether mathematics is standing on anything at all. If you want these episodes without ads, Meridian Labs on Patreon covers every channel in the group, this one included, and it comes with the full research and source archive behind each episode. Subscribe or join if you have not. Let us start where it started. There is a sentence you can write down using nothing but whole numbers, addition, multiplication, and the ordinary logical words that appear in every mathematics textbook printed in the last century. It is long, written out in full, in the primitive notation it would run to pages. But it is an arithmetical statement in exactly the same sense that 2 plus 2 equals 4 is an arithmetical statement. It contains no philosophy, it mentions no infinity you could object to. It is a claim about numbers, and nothing else. And what that sentence says, once you unwind the encoding, is that mathematics contains no contradiction. That sentence is either true or it is false. There is no third option. And no mathematician alive can prove it. Not because the proof is hard, not because nobody has been clever enough yet, because in 1930 a 24-year-old logician in Vienna proved that the proof cannot exist. Any system of mathematics strong enough to do ordinary arithmetic is, by its own internal structure, permanently barred from establishing that it does not contradict itself. If it ever manages to prove its own consistency, that proof is worthless. Because a system only proves its own consistency when it is already broken. Read that again slowly, because the shape of it is easy to miss. A consistent mathematics cannot certify itself. An inconsistent mathematics certifies itself immediately and enthusiastically. The certificate is not evidence of health. The certificate is a symptom. You have probably heard of Kurt Gödel. You have probably heard the sentence that gets attached to his name in popular science writing, which goes something like this. There are true statements in mathematics that cannot be proved. That is real, that is his first incompleteness theorem, and it is the version that made it into the culture. It is also the survivable one. It is a statement about gaps. It says the map has holes in it. Mathematicians can live with holes. They have been living with holes since Euclid. The second theorem is not about holes. The second theorem is about the ground. And the reason you have heard about the first one 100 times and the second one almost never has nothing to do with technical difficulty. The second theorem is barely more technical at all, and it falls out of the first one in about a page of additional work. The reason is that the first theorem is a curiosity you can put in a documentary, and the second theorem is a diagnosis nobody wants read aloud in the room. Here is what the second theorem actually costs. Every serious piece of mathematics done anywhere on this planet, right now. In every university and every physics department, and every cryptography lab, rests on a foundation called Zermelo-Fraenkel set theory with the axiom of choice. Working mathematicians shorten it to those three letters, ZFC, and most of them go entire careers without thinking about it, in the same way you go entire days without thinking about the load-bearing walls of the building you are sitting in. Every theorem you were taught in school can be derived inside it. Every theorem published in every journal this month can be derived inside it. It is the operating system. Nobody knows whether it is consistent. Nobody can know. Not with more funding, not with more time, not with a smarter generation of logicians. The impossibility is structural. It is a consequence of the system being strong enough to be useful in the first place. The exact feature that makes a mathematical system able to describe arithmetic is the feature that makes it unable to vouch for itself. And there is a detail buried inside that arrangement that I want to plant now, because it will not fully land until much later. If a contradiction does exist somewhere inside the foundations of mathematics, there is no mechanism anywhere in the structure that would warn us in advance. There would be no degradation, no creaking, no early symptom of any kind. The system does not fail gradually. The only signal we would ever receive is the contradiction itself, arriving one afternoon in somebody's preprint, at which point every theorem ever proved inside that system becomes simultaneously provable and refutable, retroactively, all the way back to the beginning. That is the shape of the thing. Now here is the question that runs underneath everything that follows, and I want to be honest with you at the start that it does not get answered. How would we know? Not how would we prove it? We have established that we cannot. How would we know? What could we possibly do from inside a system we cannot step outside of, using tools that are themselves part of the system, to check whether the whole enterprise is sound? Every attempt anyone has made at that question over the last 95 years has failed in a different and more interesting way, and the pattern of those failures is the actual subject of this video. Some of them failed for reasons that were obvious in hindsight. Some of them failed for reasons that took 40 years to understand. One of them, the best one, succeeded so completely that it turned out to have proved nothing at all. And the men who worked hardest on the problem paid for it in ways that are difficult to describe without sounding like I am reaching for drama, which I am not. Two of the central figures in this story died of starvation. not metaphorically. One in a Prague holding cell in the summer of 1945, and one in a Princeton hospital bed in January 1978, weighing 65 pounds, having refused food for months because he could not verify from the inside that it was safe. I will come back to that. It matters more than it sounds like it should, but to see why the second theorem hit as hard as it did, you need to understand what it hit. Because in 1930, this was not an open philosophical question that people worried about in the abstract. It was a construction project. It had a budget, a workforce, a director, and a completion date that everybody involved believed was close. The whole thing had a name. It was called Hilbert's Program, and in the summer of 1930, the people working on it believed the finish line was close enough to see. Paris, August 1900. The Second International Congress of Mathematicians convened at the Sorbonne, and on Wednesday the 8th, a 38-year-old German named David Hilbert stood up to give a talk about the future. He had prepared a list of unsolved problems. The printed version, which appeared later in the Bulletin of the American Mathematical Society, Volume 8, pages 437 through 479, contained 23 of them. He only had time to read 10 aloud. Problems 1, 2, 6, 7, 8, 13, 16, 19, 21, and 22. The second one on that list, the one he read out to a room of the most capable mathematicians in Europe, was the compatibility of the arithmetical axioms. In plain terms, prove that arithmetic does not contradict itself. He put it at number 2. Ahead of the Riemann hypothesis. Ahead of everything except the continuum problem. And for 126 years now, essentially everybody who writes about that lecture treats the second problem as a technical curiosity that got overtaken by events. That is a strange way to describe a problem that was proved unsolvable in the exact form its author intended, by a man who was in the audience of Hilbert's own conference 30 years later, and whose result Hilbert appears to have gone to his grave refusing to publicly acknowledge. Here is what nobody explains properly about why Hilbert cared. Mathematics in 1900 was in the middle of something that later got called the foundational crisis, and the word crisis is not journalistic inflation. For 2 centuries, mathematicians had been building increasingly elaborate structures on top of the concept of infinity. Georg Cantor had shown that there are different sizes of infinity, that the infinity of the real numbers is strictly larger than the infinity of the whole numbers, and that the hierarchy of infinities keeps going upward without end. It was beautiful. It was also completely uncontrolled, in the sense that nobody had written down rules for what you were and were not allowed to do with these objects. People were reasoning about collections of things without any agreed account of what a collection was. And then it broke. On the 16th of June, 1902, Bertrand Russell wrote a letter to Gottlob Frege. Frege was a German logician who had spent something close to 2 decades building the most careful, most explicit, most obsessively rigorous foundation for arithmetic that anyone had ever attempted. The second volume of his life's work, the Grundgesetze der Arithmetik, was at that moment physically in press. Russell's letter was polite, and it was short, and it pointed out that Frege's 5th basic law permitted you to construct the set of all sets that are not members of themselves, and then asked whether that set is a member of itself. If it is not. If it is not, it is. Frege had time to add an appendix. It opens with a sentence that I think is one of the most quietly devastating lines in the history of intellectual work. Hardly anything more unwelcome can befall a scientific writer, he wrote, than that one of the foundations of his edifice be shaken after the work is finished. He tried to patch the system. The patch was also inconsistent, though nobody established that until decades later. By which point, Frege had abandoned the project entirely. Think about the position that leaves everyone else in. The most careful person in the field, working in the most explicit possible notation, with every step written out, had produced a system in which you could prove anything at all. Not a system with a gap, a system with a hole straight through the middle of it, through which every false statement in the universe could walk, and he did not notice for years. Nobody noticed for years, and the question stopped being philosophical and became operational. If Frey could do that, what exactly are the rest of us standing on? Hilbert's answer, developed through the 1920s with a small group that included Paul Bernays, Wilhelm Ackermann, Jacques Herbrand, and a young Hungarian named John von Neumann, was the most audacious idea in the history of the subject. It goes like this. Split mathematics in two. On one side, put the part nobody sane can doubt. Finite objects. Concrete symbol manipulation. Statements about specific numbers you could in principle check by hand, given enough paper. Hilbert called this the finitary part, and the point of it is that it makes no reference to completed infinities at all. It is arithmetic you could do with Pebbles. On the other side, put everything else. Cantor's infinities, the real number line, all of analysis, the whole magnificent structure that had grown up over 200 years and which Hilbert refused to give up. He famously said of it that nobody would drive us out of the paradise Cantor had created for us. Now, the move. Treat the infinite part not as a description of reality, but as a formal game. A finite set of axioms, a finite set of rules for deriving one string of symbols from another. A proof becomes a physical object. It is a finite sequence of finite strings. And whether it is a valid proof is a question you can answer by checking, mechanically, symbol by symbol, without ever thinking about what any of it means. And once you have done that, the question of whether mathematics is consistent becomes a finitary question. It becomes the question of whether a certain kind of finite string, one ending in a contradiction, can be produced by these rules. That is a statement about symbol manipulation. That is the kind of thing you are allowed to reason about with Pebbles. That was the program. Use the part of mathematics nobody can doubt to certify the part everybody was worried about. Hilbert gave this new activity a name, Buis theory, proof theory, and he described it as metamathematics. Mathematics whose subject matter is mathematics itself. Nobody had ever done that before. He invented an entire discipline in order to answer one question. And it was working. Ackermann produced a consistency proof for a fragment of arithmetic in 1924. Von Neumann produced a stronger one in 1927. Each of these covered a piece of the target, rather than the whole thing. But the direction was obvious, and the momentum was real. Hilbert and Ackermann published the Grundzüge der theoretischen Logik in 1928, which laid out first-order logic in essentially the form students still learn it, and which posed one further question, the Entscheidungsproblem, the decision problem, asking whether there is a mechanical procedure that determines the truth of any mathematical statement. They thought they were assembling the final version of mathematics, a system that was complete, meaning every true statement could be proved, consistent, meaning no false statement could be proved, and decidable, meaning a machine could sort one from the other, 0 for 3, as it turned out. But that is getting ahead of the story. There is one more thing you need to know about Hilbert, and it is the thing that makes the ending land, so I want to put it in place carefully. Hilbert was not driven by curiosity here. He was driven by something closer to rage. In 1872, a physiologist named Émile Dubois-Reymond had given a celebrated lecture arguing that certain questions about nature were permanently beyond human knowledge, and he had closed it with a Latin tag that became famous across German intellectual life. ignoramus et ignorabimus. We do not know, and we will not know. It was a statement of principled surrender, and it was fashionable, and Hilbert hated it with a specificity that comes through in everything he wrote on the subject. He believed the ignorabimus was a failure of nerve dressed up as humility. He believed there was no such thing as an unsolvable mathematical problem, and he said so, repeatedly, for 40 years. He was also fighting a war on his own side of the field. L.E.J. Brouwer, the Dutch topologist, had spent the 1920s arguing that large parts of classical mathematics were meaningless and should be discarded, including proof by contradiction applied to infinite collections. If Brouwer won, an enormous fraction of existing mathematics simply evaporated. Hilbert's response in 1928 was to remove Brouwer from the editorial board of the Mathematische Annalen. Einstein, who was also on the board, described the affair as a war of the frogs and the mice, and refused to participate. That is who Hilbert was. 66 years old, the most respected mathematician in the world. At war with the philosophers on one flank and the intuitionists on the other, holding the line on a program he had staked his reputation on, and closing in on the proof that would end the argument permanently. In September of 1930, the city of Königsberg, where he had been born, made him an honorary citizen. He went home to accept it. He wrote an address for the occasion, and he arranged for a portion of it to be broadcast on local radio. The recording still exists. It runs a little under 4 minutes. You can hear his accent, and you can hear him lean into the final words with a kind of controlled fury. In place of the foolish ignorabimus, he says, let our slogan be this: we must know, we will know, win sen wissen, wir werden wissen. That broadcast went out on the 8th of September, 1930. The day before, in a conference room a short walk away, a 24-year-old graduate student with a soft voice had already destroyed the program, and almost nobody in the room had understood what he said. Kurt Gödel was born on the 28th of April, 1906, in Brünn, which was then part of Austria-Hungary and is now Brno in the Czech Republic. His father managed a textile works. The family was comfortable, German-speaking, unremarkable. At around the age of 8, he came down with rheumatic fever. He recovered completely. But at some point during the illness, or shortly after it, he read a medical description of the disease and learned that it can permanently damage the heart, and he decided that his had been damaged, and he never let go of that belief for the remaining 63 years of his life. There was no damage. Doctors told him so repeatedly, it made no difference. That is the first thing you learn about Gödel, and every biography mentions it, and almost every biography files it under eccentricity. I want to suggest that filing it under eccentricity misses what is actually happening. It is the same cognitive move that produced the theorem. A boy encounters a formal description of a system, notices that the description permits a catastrophic outcome, and concludes that because the outcome is permitted, it must be assumed. His family called him Herr Warum, Mr. Y. He arrived at the University of Vienna in 1924 intending to study physics, and switched to mathematics after attending a number theory course. His supervisor was Hans Hahn, and through Hahn he was drawn into the Vienna Circle, the group of philosophers and scientists around Moritz Schlick, who were in the process of arguing that any statement which cannot be verified by observation or reduced to logic is literally meaningless. Metaphysics, ethics, theology, all of it noise. Godel attended their meetings from 1926. He rarely spoke, and the reason he rarely spoke is that he disagreed with essentially all of it. He was a Platonist. He believed that mathematical objects exist, independently of human minds, in something like the way that mountains exist, and that when a mathematician proves a theorem they are reporting on a discovery, rather than inventing a convention. He sat in that room for years, week after week, surrounded by the most aggressive anti-metaphysicians in Europe, holding a position they would have considered mystical nonsense, and he kept his mouth shut. I find that image hard to shake. The quietest person in the room is the one who is going to break the century. His doctoral work, completed in 1929, the same year his father died, proved something genuinely reassuring. It is called the completeness theorem, and it says that for first-order logic, the basic logical machinery underneath everything else, every statement that is true in all interpretations can in fact be proved from the axioms. Logic itself has no gaps. It was published in the Monatsheftì from Mathematik und Physik, volume 37, pages 349 to 360, and it was exactly what Hilbert's people wanted to hear. Which is worth pausing on. Gödel's first major result was good news for the program. He was not an opponent. He was not a Brouwer-style objector trying to burn the field down. He was a young man working inside Hilbert's own framework, using Hilbert's own tools, on Hilbert's own question, and the reason his result cut so deep is that it came from inside the building. By the summer of 1930, he had the other one. On the 26th of August, 1930, he sat in a Viennese cafe with Rudolf Carnap and told him about it. We know the date because Carnap kept a diary and wrote it down. Carnap's entry is brief and slightly puzzled. He does not appear to have grasped at that table what he had just been told. 10 days later, the three of them travelled north to Königsberg for the second conference on the epistemology of the exact sciences, running from the 5th to the 7th of September. Gödel gave a short talk on the second day about his completeness theorem, the good news one. He said nothing about the other result. On the third day, the 7th of September, there was a closing roundtable discussion on the foundations of mathematics. The transcript of that discussion survives, and it is one of the strangest documents in 20th century intellectual history, because in the middle of it, without preamble, Gödel says that one can even give examples of statements which are contentiously true but unprovable in the formal system of classical mathematics. That is it. That is the announcement. It is a single contribution to a panel discussion, delivered in the flat register of a man correcting a minor point of order. The discussion moved on. The published proceedings record almost no reaction. Most of the room appears to have either not registered what was said, or assumed they had misunderstood it, and given what was being claimed, assuming you had misunderstood it was the reasonable response. One man in that room understood immediately. John von Neumann, who was 26 years old, who had already produced one of the consistency proofs the program was built on, and who had the fastest analytical mind anyone who met him could remember encountering, went up to Gödel afterwards and asked him to explain it again in detail. And the next morning, in a different building in the same city, Hilbert stepped up to a microphone and told a radio audience that we must know and we will know. The two events are separated by less than 24 hours and a few hundred meters. There is no evidence that Hilbert heard about Gödel's remark before he spoke, and no evidence that Gödel and Hilbert ever met at all. That week or any other, they were in the same small city, working on the same problem on consecutive days, and the message did not travel. I have seen that timing described as tragic irony in a dozen popular accounts, and it is usually where those accounts stop, because it makes a clean ending. But it is nowhere near the ending. It is barely the beginning, and the reason is that what Gödel said at that round table was not the result that killed Hilbert's program. The result he announced was the first incompleteness theorem. True statements without proofs. That is serious, but a determined optimist could survive it. You could argue that the unprovable statements are exotic, artificially constructed, of no interest to working mathematicians. People did argue exactly that for years. The result that killed the program was the one he had not announced yet. It was sitting in his notes, It was going into the paper he was about to submit, and it does not concern exotic statements at all. It concerns the single statement Hilbert had staked the entire enterprise on. The paper went to the Monatschrift from Mathematik und Physik on the 17th of November, 1930. It appeared in 1931 in volume 38, pages 173 to 198, under the title On Formally Undecidable Propositions of Principia Mathematica and Related Systems 1. Note the number at the end of that title. Roman numeral 1, Part 1. Godel promised a second part. He said so explicitly in the paper, and he said the second part would contain the full proof of the result we are actually here to talk about, because in Part 1 he had only sketched it. 2 paragraphs. An outline, essentially a promissory note, sitting near the end of a paper that had already changed everything else. Part 2 never appeared, not in 1932, not in 1940, not ever. And here is where I want to correct something that almost every account of this story gets wrong, including accounts written by people who should know better. Godel did not prove the second incompleteness theorem in 1931. He announced it. He sketched the argument in a way that convinced the handful of people qualified to evaluate it, and then he moved on and never wrote it up properly. The first complete, rigorous, published proof of the theorem that bears Godel's name appeared 8 years later, in 1939, in the second volume of a 2-volume work called the Grundlagen der Mathematik. The name on the cover is Hilbert and Bernays. The book was written almost entirely by Bernays. Paul Bernays was Hilbert's assistant. He was the man who had spent the 1920s doing the technical labour of Hilbert's programme, the actual proof theory, the machinery. He was dismissed from Göttingen in 1933 under the racial laws, being Jewish, and he continued the work from Zurich. And the thing he completed, carefully, over years, working from Godel's 2-paragraph sketch, was the formal demonstration that the project he had given his career to was impossible. He wrote out the proof that his own life's work could not be done. Then he published it under his dead program's founder's name. Nobody talks about Bernays. He gets a line in the standard histories, usually as an assistant, occasionally as a co-author. The 3 conditions that make the second theorem work are known in the literature as the Hilbert-Bernays conditions, or sometimes the Hilbert-Bernays LB conditions. And if you ask a working mathematician who Bernays was, you will mostly get a shrug. But before any of that could happen, before the sketch or the proof or the 8 years in between, Gödel had to solve a problem that had defeated everyone who looked at it. He had to make arithmetic talk about itself, and the way he did it is the single most elegant piece of construction in the history of logic. It is also, once you see how it works, considerably more disturbing than the theorem it was built to prove. The obstacle was this: a formal system is a machine for proving statements about numbers. It does not have opinions about itself. It has no vocabulary for the words proof, axiom, provable, consistent. Those words live outside the system, in the metamathematics, where Hilbert had put them deliberately. From inside arithmetic, the question of whether arithmetic is consistent cannot even be posed. There is no formula that asks it. It is a noise from another room. To prove anything about what a system can and cannot do, using only the resources of that system, you first have to smuggle the entire vocabulary of proof theory into the language of whole numbers. Godel's method takes about 2 pages to set up, and it is so simple that people who encounter it for the first time often assume they have missed something. Assign a number to every symbol. The symbol for 0 gets 1. The successor function gets 3. The negation sign gets 5. The or sign gets 7. the universal quantifier gets 9. Brackets, variables, the equals sign, each gets its own number. There are only finitely many symbols, so this takes a moment. Now take any formula, which is just a string of those symbols in order, and encode the whole string as a single number. You do it with prime numbers. Take the sequence of prime numbers 2, 3, 5, 7, 11, 13, and so on, and raise the first prime to the power of the first symbol's number, the second prime to the power of the second symbol's number, and so on down the string, then multiply the whole lot together. Because every whole number has exactly one prime factorization, and there are no exceptions to that, the process runs backwards without ambiguity. Given the number, you can recover the formula. Given the formula, you get exactly one number. The encoding is perfect. I want you to feel how violent this is in terms of size, because the elegance hides it. Take a formula 5 symbols long, with the symbol codes 1, 2, 3, 4 and 5. 2 to the first, times 3 squared, times 5 cubed, times 7 to the fourth, times 11 to the fifth. That is 870 billion, 37,764,750. A 12-digit number for a formula 5 symbols long. Push it to 8 symbols with realistic codes and you are already at 61 digits, which is a few thousand times the number of atoms in the sun. A formula of moderate length, the kind of thing that occupies half a line in a textbook, has a code number that would take you an afternoon to read out loud. And a proof is a sequence of formulas which gets encoded the same way, by raising primes to the power of the numbers you just built. The code number of even a short proof has a decimal expansion you could not write down inside the solar system, none of which matters even slightly, because you never have to write it down. The numbers exist. That is all Godel needed. Because now watch what happens. The statement this string of symbols is a well-formed formula has become a statement about a number. The statement this sequence of formulas obeys the rules of inference at every step has become a statement about a number. The statement the formula with number x is derivable from the axioms by the proof with number y has become an ordinary arithmetical relation between two whole numbers. It is a relation you could in principle check with long division and patience. Godel builds these up one at a time in the paper, in a numbered list. It runs to 46 items. The first 45 are what are called primitive recursive relations, which is a technical way of saying that each one can be computed by a procedure that is guaranteed to halt, with the number of steps known in advance. Item 1 is the relation x divides y. By item 45 he has the relation y is a proof of the formula x. Item 46 is where the flaw drops out. Item 46 is provability. Not y is a proof of x, but x is provable, meaning there exists some y somewhere that is a proof of it. And that one is not primitive recursive, and it cannot be made primitive recursive, and the reason is the word exists. To check whether a specific y proves x, you look at y and grind through it, and you are done. To check whether any y at all proves x, you have to search, and you have no idea how far to search, because there is no bound on the length of a proof. That gap between item 45 and item 46 is the entire theorem. Everything else is bookkeeping. Checking a proof is finite. Finding a proof is not. And a system that can talk about the first, but has to open an unbounded search for the second, has, without anyone intending it, acquired a blind spot with a very specific shape. Now Godel does the thing that got his name into the culture. Using the encoding, he constructs a formula. Call it G. And G, when you translate it back out of the arithmetic and into ordinary language, says the following. There is no number that is the Gödel number of a proof of the formula with Gödel number n, and by a construction called the diagonal lemma, which is the technical heart of the paper and which lets you build a sentence that refers to its own code number. The number n turns out to be the Gödel number of G itself. G says that G is not provable. Here is where I have to stop and correct something, because the popular version of this has been wrong for 90 years, and the wrong version is doing real damage to how people think about the result. You will constantly hear that Gödel's sentence is a version of the liar paradox. This statement is false. You will hear that the whole thing is a clever piece of self-referential trickery, a logician's parlour trick, and that the theorem tells us something about the dangers of self-reference, rather than anything about mathematics. That reading is wrong, and Gödel personally shot it down inside the original paper, before anyone had a chance to make the mistake in print. The liar sentence is about truth. It says of itself that it is false, and that is a genuine contradiction, and the standard response is that such a sentence is not well formed. Gödel's sentence is about provability, which is a completely different kind of property. Provability is a mechanical, checkable, arithmetical relation. It is not a semantic notion at all. And a sentence that says of itself that no proof of it exists carries no contradiction at all. If no proof exists, the sentence is simply true. Gödel put it like this in the paper. Contrary to appearances, he wrote, such a proposition involves no faulty circularity, and he explained why. The sentence does not start out talking about itself. It starts out asserting that a certain purely arithmetical property holds of a certain specific number, in the same way you might assert that 17 is prime. It is only afterwards, and Gödel's own phrase for this is that it happens as it were by accident, that this specific number turns out to be the code of the very sentence making the assertion. Nobody designed the self-reference in. It is a fixed point that falls out of the arithmetic whether you want it or not, and this matters enormously for the second theorem, so hold on to it. If Gödel's construction were a trick, you could ban the trick. Logicians spent decades trying. Every attempt to outlaw the self-reference either destroyed the system's ability to do arithmetic or failed to stop the construction. Because the construction is not using a loophole, it is using multiplication. What happens to G then? Suppose the system proves G. Then there is a proof of G. But G says there is no proof of G, and the system just proved G. So the system has proved something false, and a system that proves something false about whole numbers is a system that will prove anything at all. Therefore, if the system is consistent, it cannot prove G. Suppose instead the system proves the negation of G, meaning it proves that a proof of G does exist. Then, if the system is not lying, some specific number is the code of that proof. But the system can check any specific number, one at a time, and confirm that it is not the code of a proof of G. Because we have just established that no proof of G exists. The system would therefore be asserting that a proof exists while simultaneously being able to refute every individual candidate. That state is called a mega-inconsistency, and Gödel needed to assume it away, which was the one soft joint in the original argument, and it did not survive long. In 1936, an American logician named J. Barclay Rosser published a modification in the Journal of Symbolic Logic, Volume 1, Issue 3, pages 87 to 91, that removes the assumption entirely. Rosser's version of the sentence says, roughly, that for any proof of me there is a shorter proof of my negation. With that adjustment, the theorem needs only plain consistency. The soft joint is gone. G is unprovable, and its negation is unprovable. The system cannot decide it in either direction. And yet you, sitting there, can see that G is true, because you can see that it asserts its own unprovability, and you have just watched the proof that it is in fact unprovable. That last observation has launched 60 years of argument about whether human minds exceed machines, and we will come back to it, because Gödel himself had a position on it, and his position is not the one the popular versions attribute to him. But the first theorem, for all the noise it generated, leaves the program bruised rather than dead. Hilbert's people could reasonably say that G is a manufactured curiosity, that no working mathematician would ever care about it, and that the consistency proof they were actually after has nothing to do with weird self-referential sentences. And then, Gödel writes the two paragraphs. Near the end of the 1931 paper, after the main theorem is established, Gödel makes an observation that reads on first pass like housekeeping. The entire argument he has just given, the whole demonstration that G is unprovable, is itself a finitary argument. It manipulates finite strings, it performs bounded checks, it contains no appeal to completed infinities, no controversial reasoning, nothing that Hilbert or Brouwer or anyone else would object to. That was deliberate. Gödel constructed it that way precisely so that his critics could not accuse him of using the disputed methods to attack the disputed methods. But if the argument is finitary, then the argument can be encoded. Everything finitary can be encoded. That was the whole point of Gödel numbering. Then, encode it. Take the proof that if the system is consistent, then G is unprovable, and write it out inside the system in the language of whole numbers. What you get is a formula the system can derive, and that formula says the following. If the system is consistent, then G. The system can prove that conditional. It cannot prove the consistency itself. It can prove that consistency would deliver G. Now put the two results next to each other and watch what happens. The system proves that consistency implies G, and we have already established that the system cannot prove G. Therefore, the system cannot prove consistency, because if it could, it would immediately chain the two together and derive G, which it cannot do. That is the second incompleteness theorem. It is 4 sentences long. Everything that makes it work was already built for the first one, and the statement it says you cannot prove is not exotic at all, which is what makes this different in kind rather than degree. G was strange, self-referential, arguably artificial. The consistency statement is the single sentence Hilbert had organised an entire research programme around. It is written down in his second Paris problem. It is the thing Ackermann and von Neumann had been chipping away at for 6 years. It says that there is no number which codes a proof of a contradiction, and it is as ordinary an arithmetical claim as any you will meet. Hilbert wanted to prove it using finitary methods. Gödel's observation is that finitary methods are exactly the methods that can be run inside the system. Therefore, a finitary consistency proof, if one existed, would be a proof the system could carry out about itself. Therefore, it does not exist. The very property that made Hilbert's methods safe is the property that makes them insufficient. Nobody had weakened the program or delayed it. They had shown it was attempting something that cannot happen. There is a subtlety here that took another 25 years to nail down properly, and I want to include it because it is the kind of detail that separates the real story from the version you get in a lecture. For the encoding argument to work, the way the system talks about its own provability has to behave sensibly. Specifically, 3 things have to hold. If the system proves something, it has to be able to prove that it proves it. If it proves an implication, it has to respect that implication inside the provability predicate, and it has to be able to prove that first property about itself. The first 2 were laid out by Bernays in 1939. The third was isolated in 1955 by a British logician named Martin L.B., and they are known collectively as the derivability conditions. They are not decoration. They are the load-bearing structure, and the fact that it took 2.5 decades after the announcement to get them written down cleanly tells you that the second theorem was understood in outline long before it was understood in detail. Meanwhile, in November of 1930, something happened that has been reported carelessly for decades, and which I think is the most human moment in the whole story. Von Neumann went home from Königsberg and thought about what Gödel had said, and within about 10 weeks he had derived the second incompleteness theorem himself, independently from the first one. On the 20th of November, 1930, he wrote to Godel to tell him about it, describing it as a remarkable consequence. 3 days earlier, on the 17th, Godel had already submitted the paper containing it. Von Neumann withdrew his claim immediately and completely. He never published his version. Nobody knows what his proof looked like, because the manuscript does not survive. And the reconstruction attempts published in the last few years are exactly that, reconstructions. He wrote again on the 12th of January, 1931, and in that exchange he stated the result in a stronger form than Godel had, effectively arguing that the consistency of mathematics as such was unprovable, and the two of them disagreed about how far the conclusion reached. You will read in many places that von Neumann abandoned logic on the spot, walked away from foundations forever, and turned to the applied work that made him famous. That is a compression of something real into something tidier than it was. He did move away from foundational research, and the timing is not a coincidence. But he did not stop thinking about it. He lobbied for years to get Godel a permanent position in Princeton, and when he did, he wrote that Godel was absolutely irreplaceable, and that he was the only mathematician about whom von Neumann dared make that assertion. In March of 1951, presenting Godel with the first Albert Einstein Award, von Neumann described the achievement in modern logic as singular and monumental, and said it was more than a monument, that it was a landmark which would remain visible far in space and time. That is a man who did not get over it. Now Hilbert. And here I have to be careful, because this is the part of the story where the popular retellings go furthest off the record. You will find, in books and articles and video essays, a vivid scene in which Hilbert is told the news and is visibly devastated, or in which von Neumann stands up at a faculty meeting and calls Godel the greatest logician since Aristotle. Those scenes read well. They also appear to originate in a novel. John Casti published a book in 2003 called The One True Platonic Heaven, which is explicitly a work of fiction built around real figures at the Institute for Advanced Study, and material from it has leaked into non-fiction retellings without anyone flagging the source. What we actually have is thinner, and I think more revealing. Bernays, in correspondence with Hilbert's biographer Constance Reed decades later, reported that Hilbert was angry about the result. Angry, not devastated, not enlightened. Angry. In the way a man is angry when someone tells him the load-bearing wall is not there. There is no record of Hilbert ever publicly acknowledging Godel's theorems. None. He did not cite them, did not discuss them in print, did not mention Godel by name in any published work I can find. What he did instead was try to move the goalposts, and he did it fast. In 1931, the same year the paper appeared, Hilbert published 2 responses. One in the Mathematische Annalen, volume 104, pages 485 to 494. Another in the Göttingen proceedings. In both, he proposed extending the rules of the system with something called an omega rule, which says that if you can establish a statement for 0, and for 1 and for 2, and for every specific number you care to name, you may then infer the general statement for all numbers. That is a rule with infinitely many premises. You cannot apply it in finite time. It is not a rule a person or a machine can use, and it was not a repair to the program so much as a redefinition of what counted as a proof, introduced by a man who had spent 30 years insisting that proofs are finite objects you can check by hand. Godel, in correspondence with Bernays, showed that even with the omega rule bolted on, the extended system remained incomplete. You can climb, but the ceiling climbs with you. Not everyone reacted with Hilbert's dignity. Ernst Zermelo, whose set theory is the Z in the three letters everyone now uses, entered into correspondence with Gödel in 1931 and simply did not understand the proof. He read the provability, predicate as a truth predicate, concluded that Gödel had rediscovered a paradox he already knew about, and stayed hostile. Godel wrote back patiently explaining the distinction, in a letter that quietly anticipates Tarski's theorem on the undefinability of truth. Zermelo was not persuaded. He was 60 years old, and he had made his contribution, and he could not see it. Wittgenstein, who was in a category of his own, wrote a set of remarks on the theorem that are so hostile and so apparently confused that the standard scholarly reaction for 50 years was that he had failed to understand a technical result. In 2000, Juliet Floyd and Hilary Putnam published a defense arguing there was a real insight buried in there. That defense has itself been contested since by several logicians. The argument is not resolved. Godel, for his part, read Wittgenstein's remarks and dismissed them. David Hilbert died in Göttingen on the 14th of February, 1943, in the middle of a war that had emptied his department of nearly everyone who mattered. Fewer than a dozen people attended the funeral. The mathematical community he had built was scattered across 3 continents, most of it in flight from a government he had lived long enough to see take power. His gravestone in Göttingen carries the 2 sentences from the radio broadcast. We must know. We will know. He is buried under a claim that a 24-year-old had disproved 13 years before he died, in the city where he was born, on the day before he said it. And the program was dead. But mathematics was not, and mathematicians still had to get up in the morning and do their jobs, and the question of what exactly they were standing on had now become considerably more urgent than it had been in 1900. Which brings us to the one man who found a way through, and to what his solution actually cost. Gerhard Gentzen was born on the 24th of November, 1909, in Greifswald on the Baltic coast. He went to Göttingen. He was Bernays' student until 1933, when Bernays was dismissed under the racial laws and Hermann Weyl took over the formal supervision, and he was, by every account of people who worked with him, one of the 2 or 3 most naturally gifted proof theorists who has ever lived. In 1936, at the age of 26, he published a proof of the consistency of Peano arithmetic. Peano arithmetic is the standard formal system for the whole numbers. Named for Giuseppe Peano, it is the axiomatization every logic course starts with, and it is comfortably strong enough for Gödel's theorems to apply. Gentzen proved it consistent, with no conditions and no partial results attached. He wrote down a proof that no contradiction can be derived in Peano arithmetic, published it in the Mathematik-Annalen, volume 112, and it has stood up to 90 years of scrutiny. It is correct. Which should be impossible. Something has to give. What happened is that Gentzen used a tool that Peano arithmetic does not contain. His method assigns an ordinal number to every proof, and then shows that if a proof ended in a contradiction, you could always transform it into a proof with a strictly smaller ordinal. Since you cannot descend forever through a well-ordered collection, no such proof exists. It is an argument by infinite descent, and it is genuinely lovely. The ordinals he needed reach up to a specific one called epsilon naught, and I want to give you a feel for it, because the name makes it sound larger than it is, and the smallness is the point. Start with omega, the first infinite ordinal, the order type of the whole numbers laid end to end. Now form omega to the power of omega. Then omega to the power of that. then omega to the power of that. Keep going, forever, stacking exponentials. The thing you approach but never reach in finitely many steps is epsilon naught. It is the smallest ordinal that is equal to omega raised to its own power. It is countable. It is, by the standards of set theory, tiny. Set theorists work daily with objects so much larger than epsilon naught that the comparison is meaningless. And yet, the principle that you can perform induction all the way up to it is a principle that Peano arithmetic cannot establish. Gentzen proved that too in his habilitation work, which appeared in 1943. Arithmetic can prove induction up to any ordinal below epsilon naught. It cannot get to epsilon naught itself. And the second incompleteness theorem survives intact. Gentzen's result confirms it exactly, with the precision of a measurement. Gentzen did not sneak past Gödel. He located the boundary and reported its coordinates. Which brings me to a correction I need to make, because this one shows up even in careful writing. You will read that Gentzen proved arithmetic is consistent. Full stop, no qualification, sometimes framed as a rescue of Hilbert's program. That framing is doing something misleading, and here is the shape of the problem. Gentzen's proof establishes that arithmetic is consistent, provided that transfinite induction up to epsilon naught is legitimate. It reduces one assumption to another assumption, and the assumption it reduces to is, in the relevant technical sense, stronger than the one it started with. He did not build a floor. He proved that if you are standing on a specific higher floor, the one below it holds. You can now ask the obvious question, and the obvious question is the one that should keep you up. What is that higher floor standing on? There is a system whose consistency would justify transfinite induction to epsilon naught, and that system's consistency cannot be established inside it either, and to establish it you go up again, and the ordinals get larger, and the systems get stronger. And at every level the same thing happens. Each floor can certify every floor beneath it. No floor can certify itself. The whole structure is held up by the floor above. Go up as far as you like. There is no ground. This field still exists. It is called ordinal analysis, and it is one of the more technically formidable areas of mathematical logic, and its practitioners have computed the proof-theoretic ordinals for systems well beyond Peano arithmetic. Progress is real, and it is slow. Full second-order arithmetic remains beyond reach after decades of work. And for the system that actually underwrites working mathematics, the one with the 3 letters, there is no ordinal analysis at all, not a partial one. Nobody is close. Gentzen never saw where any of it went. There is a part of his biography that gets skipped in the histories that treat him as a martyr, and skipping it is a disservice. So here it is. Gentzen joined the Sturmabteilung in November of 1933 and the Nazi Party in 1937. During the war he worked at the German Aeronautical Research Institute in Berlin on calculations connected to the V2 program. In 1943 he took a teaching post in Prague. He was, on the documentary record, a participant rather than a bystander, and the same year he published the work extending his consistency results. He was drawing a salary from a state that was operating extermination camps. In May of 1945, following the Prague uprising, German nationals in the city were rounded up. Gentzen was taken into custody. He was held for 3 months, in conditions that his fellow prisoners later described as severe, and he died on the 4th of August, 1945. The cause was starvation. He was 35. The man who had gone furthest into the question of what mathematics rests on, the only person who had produced anything resembling an answer, died of hunger in a cell in a city he had been sent to by a regime he had joined, 4 months after the war ended in Europe. Hold on to that. it is going to happen again, in a different country, to a different man, 33 years later, and for a reason that is going to make the coincidence stop feeling like a coincidence. But before that, there is one more escape route to close, and it is the cleverest one anyone found. In 1960, Solomon Pfefferman published a paper in Fundamenta Mathematicae, volume 49, pages 35 to 92, called Arithmetization of Metamathematics in a General Setting. And what Pfefferman did was ask a question nobody had thought to ask carefully. When we say the system cannot prove its own consistency, which consistency statement do we mean? Because there is not just one. The statement there is no proof of a contradiction, has to be written down in the formal language. And to write it down you have to fix a way of describing which formulas count as axioms. There are many ways to do that, and they can be mathematically equivalent while behaving completely differently inside the probability predicate. Pfefferman constructed one. He built an alternative description of the axiom set, technically legitimate, describing exactly the same axioms, under which the system does prove its own consistency. Take a moment with that, because it sounds like the theorem just broke. It did not. Pfefferman's provability predicate satisfies the first two derivability conditions and fails the third, and what his construction actually proves is subtler and more interesting than a counterexample. It shows that the second incompleteness theorem is a fact about systems together with the way those systems describe themselves, rather than a fact about the systems alone. Change the self-description in a sufficiently perverse way, and the theorem loses its grip, because the sentence you are now proving is no longer really saying what you think it is saying. Logicians call this the intentionality problem, and it has never been fully resolved. There is no agreed general criterion for what makes a consistency statement natural. There are proposals, nobody thinks any of them is definitive, which means the honest formulation of the second theorem is uglier than the one that gets quoted. The honest version says that a system can never prove its own consistency when the consistency statement is expressed in a way that means what we intend it to mean, and we cannot say precisely what that condition amounts to. We can only recognize violations when we see them. I find that genuinely uncomfortable, and I have not seen a treatment of it aimed at a general audience anywhere, which is its own small indictment. There is one more thing worth clearing up before we leave the technical machinery, because it gets misused constantly. The incompleteness theorems do not apply to every formal system. They apply to systems meeting three conditions. The system must be consistent. Its axioms must be effectively listable, meaning a machine could enumerate them. And it must be strong enough to interpret a modest amount of arithmetic, roughly the ability to add and multiply. Drop the arithmetic and the theorems evaporate. Presburger arithmetic, which has addition but no multiplication, was proved complete and decidable by Mojez Presburger in 1929, the year before Königsberg. Every statement in it can be settled by an algorithm. The first-order theory of real closed fields, which covers a great deal of classical geometry, is likewise complete and decidable, a result of Tarski's. Multiplication is the poison. Addition alone is safe. The moment a system can multiply, it can encode sequences, and once it can encode sequences it can talk about itself, and once it can talk about itself the ceiling appears. Anyone who tells you Godel proved that all systems are incomplete, or that logic itself is broken, or that this shows truth is relative, is telling you something the theorems do not say. The theorems are precise. Their scope is precise, and the scope happens to include, without exception, every formal system anybody actually uses to do mathematics, which brings us out of the 1930s and into the room you are actually sitting in. Here is the situation as it stands in 2026. The foundation of mathematics is Zermelo-Fraenkel set theory with the axiom of choice. Zermelo wrote the first version in 1908, partly as a response to the paradoxes that had killed Frege. Abraham Fraenkel and Thorolf Skolem independently added the replacement axiom in 1922. The axiom of choice was bolted on after an argument that lasted decades and which is still not entirely over. The whole thing amounts to about 9 axioms depending on how you count, and it fits comfortably on one page. From that page, you can derive everything. That is not a figure of speech. Every theorem in every mathematics journal published this month can, in principle, be reconstructed as a formal derivation from those axioms. The real numbers are built there. Calculus is built there. The theory of groups, the theory of manifolds, probability, topology, the mathematics underneath quantum field theory and cryptography and machine learning and the models that price the bonds in your pension. All of it is downstream of one page. And whether that page contains a contradiction is a question that cannot be answered from inside mathematics. I want to close off the escape hatch that gets reached for at this point, which is to say that this is an abstract worry about abstract objects, and that arithmetic itself is surely fine. It is not an abstract worry, and here is why. The statement that Zermelo-Fraenkel set theory is consistent can be written as a statement purely about whole numbers. It says that no whole number is the code of a derivation of a contradiction from those axioms. That is a claim in the same logical class as the claim that no whole number is a counterexample to some polynomial equation. It is checkable in principle, one number at a time forever. There is a specific finite number that witnesses its falsehood, and that number exists right now, and it is either there or it is not. The question of whether the foundations of mathematics are sound turns out not to be a question about infinity at all. It asks about one particular whole number, and whether or not that number exists. The obvious move, then, is to go up. If the system cannot certify itself, use a stronger system. This is exactly what set theorists do, and it has produced one of the strangest structures in intellectual history. Add to Zermelo-Fraenkel set theory the assumption that a certain kind of very large infinite number exists, called an inaccessible cardinal. It is inaccessible in the sense that you cannot reach it from below by any of the operations set theory provides. Add that axiom, and the resulting system proves that Zermelo-Fraenkel set theory is consistent. The certificate you wanted is now available. You have it in hand. You just cannot certify the thing that issued it. Add a stronger assumption. Measurable cardinals. That system proves the consistency of the inaccessible system, and of the base system, and of everything underneath. It cannot prove its own. Go further. Wooden cardinals, supercompacts, huge cardinals, each stronger than the last, each certifying every level below, and none certifying itself. Set theorists have been mapping this hierarchy for 60 years, and it now extends further than anyone in 1960 expected, and it has a property that nobody has been able to explain, which I think is the single most under-discussed fact in modern mathematics. The hierarchy is linearly ordered. Every large cardinal axiom anyone has ever proposed, hundreds of them, arising from completely unrelated motivations in completely unrelated areas of set theory, sorts into a single line by consistency strength. Given any two, one of them proves the consistency of the other. There is no branching. There are no incomparable pairs sitting off to the side. There is no theorem that says this must be so. It is an empirical observation about a mathematical object, which is already an odd sentence to write, and it has held for 6 decades across every axiom anyone has thought of. Nobody knows why. There are conjectures. There is no proof. The most honest thing anyone has said about it is that it looks as though the axioms are describing something that was already there, with a structure of its own, which the mathematicians are discovering rather than choosing. Gödel would have liked that a great deal. He believed exactly that, in that room in Vienna, with his mouth shut, for years. Now, a correction, because these two things get run together constantly, and they are different in kind. You have probably heard that Godel and Paul Cohen proved the continuum hypothesis undecidable, and you have probably heard it described as another example of incompleteness. The continuum hypothesis is Cantor's conjecture that there is no size of infinity strictly between the whole numbers and the real numbers. It was the first problem on Hilbert's Paris list. Godel showed in 1940 that it cannot be disproved from the standard axioms. Cohen showed in 1963, using a method called forcing which he invented for the purpose, that it cannot be proved either. That is independence, and it is not the same phenomenon as incompleteness in Gödel's sense, and treating them as the same thing obscures what is actually strange about each of them. The Gödel sentence is unprovable because of self-reference and the structure of probability. It is manufactured, its content is about the system. The continuum hypothesis is a natural mathematical question that was asked in 1878 about sizes of infinite sets, with no self-reference anywhere in it, and the reason it cannot be settled is that the axioms genuinely do not pin down what the universe of sets looks like. Different models satisfy the same axioms and disagree about the answer. One is a limit on what a system can say about itself. The other is a discovery that the system was never specific enough to have an opinion. Both are cracks. They are not the same crack, and merging them makes the whole subject sound like a single vague warning about limits, rather than a set of precise and different structural facts. We now have a foundation nobody can verify, a hierarchy above it with no top, and no flaw anywhere in the structure that supports itself. And here is the part that I think should genuinely bother you. Essentially, no working mathematician thinks about any of this. Ever. I do not mean that as an insult. It describes professional practice accurately. A number theorist proving a result about elliptic curves is not consulting the axioms of set theory, in the same way that a structural engineer is not deriving the behaviour of steel from quantum mechanics. The abstraction holds. It has held for 100 years. The practice works. But when you ask why they believe the foundation is sound, the honest answers are not mathematical answers. They are that nobody has found a contradiction yet, that the systems have been used intensively by very clever people for a century, that the relative consistency results are reassuring, that mathematics feels like it is about something, and things that are about something do not usually contradict themselves. Every one of those is an empirical argument, not one of them is a proof. And they are the same arguments that would have been available to a competent logician in 1900 sitting in a room with Fragi's Grundgesetze on the desk 6 weeks before Russell's letter arrived. Before we ask whether it has ever actually happened, you need to know what would happen. Because the failure mode here is not what people assume, and the assumption is doing a lot of work in keeping everybody calm. The natural picture of a contradiction in mathematics is a localized fault. Somewhere deep in set theory there is a bad spot, and the theorems near it are unreliable, and the rest of mathematics carries on fine because it never goes near the damaged region. Number theory would be unaffected. Your bank would be unaffected. It would be a specialist problem for specialists. That picture is wrong. And the reason it is wrong is a result that medieval logicians knew, and that Clarence Irving Lewis formalised in the early 20th century. It is called the principle of explosion. Take any contradiction, any at all. Say a system proves that 2 plus 2 equals 4, and also proves that 2 plus 2 does not equal 4. Now watch how far that reaches. From the first statement, 2 plus 2 equals 4, you may infer the disjunction 2 plus 2 equals 4, or the Riemann hypothesis is true, That inference is valid in every standard logic, because if you already have one half of an either-or claim, the whole claim follows regardless of what you put in the other half. You could put anything there. The moon is made of tungsten. Your name is not your name. Now take the second statement. 2 plus 2 does not equal 4. Combine it with the disjunction you just derived. One of the two branches is ruled out. Therefore the other branch holds. Therefore the Riemann hypothesis is true. And you can run that with any sentence you like in the second slot. Every statement in the language becomes provable, all of them at once, including every statement and its negation together. A single contradiction anywhere in the foundations, therefore, does not produce a damaged region. It produces a system in which the word proof has no content at all, because everything is proved, because proof no longer distinguishes anything from anything. Every theorem in every journal in the world would be a theorem. So would its opposite. The library would still be there, it would just have stopped meaning anything. That is why the second incompleteness theorem is not an academic curiosity about self-reference. If it were possible for mathematics to fail gracefully, to have an error you could isolate and root around, then not being able to verify the foundations would be a manageable risk, like any other engineering risk. It is not manageable, because there is no partial version of the failure. The system is sound or it is noise, with nothing in between, and we are structurally prevented from finding out which. There is one proposed escape, and I want to give it its due, because it is serious work by serious people, and it usually gets ignored entirely. Paraconsistent logics, developed principally by Newton da Costa in Brazil from the 1960s and by Graham Priest, reject the explosion principle outright. They redesign the rules of inference so that a contradiction stays local, so that from a contradiction about one thing you cannot derive arbitrary conclusions about everything else. There are worked out paraconsistent set theories. Some of them can accommodate the very paradoxes that killed Frege without collapsing. Working mathematicians have almost entirely declined to adopt them. And the reason given is not usually a refutation. The reason given is that the cost is too high. To block explosion, you have to give up inference rules that mathematicians use constantly and consider obvious, and the mathematics you can do in the resulting system is meaningfully weaker, which amounts to saying that we have looked at the emergency architecture, priced it, decided it costs more than it is worth, and gone back to the building we cannot inspect. That may well be the correct call. It is not a proof of anything, and it is worth being clear that it is a decision about convenience, made in the absence of information, rather than a demonstration that the risk is small. Which raises a question that the reassurance industry around this topic never asks. Has this actually happened? Not in principle, but in fact. Has a serious foundational system, proposed by a serious person, and believed by serious people, ever turned out to contain a contradiction? It has. 4 times that I can document properly, and the details of each one are worse than the summary. Start with Frege, because we have already met him, and because the timing is the part that should stay with you. He was not a crank. He was the most rigorous logician of his generation, working in the most explicit notation anyone had ever devised, and the specific virtue everyone praised him for was that he wrote out every single step so that no unexamined assumption could hide anywhere. The inconsistency lived in his 5th basic law for roughly 9 years, in print, read by the small number of people capable of reading it, and none of them saw it. Russell saw it because Russell was looking for it, having found a similar problem in his own work. Frege's attempted repair, added in the appendix, was also inconsistent. Stanisław Leniewski established that some years later. Frege did not learn of it in a way that changed anything. He abandoned the Logicis project and spent his last years arguing that arithmetic should be founded on geometry instead. Second case. In 1971, Per Martin Elf published a formulation of what is now called intuitionistic type theory. It was designed to be a foundation for constructive mathematics, and it was designed with care, and among its features was a rule permitting the collection of all types to itself be a type. In 1972, Jean-Yves Girard proved it inconsistent. 1 year. Girard found a way to encode a paradox of set theory into the type structure and derive a contradiction. Martin Elf accepted the result immediately, removed the offending rule, and replaced it with an infinite hierarchy of universes, which is the version that survives today and which underpins a large part of modern computer-assisted proof. Third case, and this one is the sharpest because it is the only time a large cardinal axiom has been outright killed. In 1967, William Reinhardt proposed a very strong axiom of infinity, describing a cardinal so large that its existence would imply a certain kind of self-similarity in the entire universe of sets. It sat at the top of the hierarchy. People worked with it. In 1971, Kenneth Cunan published a paper in the Journal of Symbolic Logic, Volume 36, Issue 3, pages 407 to 413, proving that no such cardinal can exist. Not that it was unlikely, or that its consistency was doubtful. That standard set theory outright refutes it. Think about what that means for everything above it. Set theorists had been climbing a ladder of stronger and stronger assumptions, using each rung to certify the ones below, and one of the rungs near the top turned out not to be there. It was the first time a proposed large cardinal axiom had been refuted rather than merely doubted. It has not happened again. Nobody has an argument that it will not. Fourth case is the longest running, and it ended in a way I did not expect when I started reading about it. In 1937, Willard Van Orman Quine proposed an alternative set theory called New Foundations. It avoided the paradoxes by a completely different route from Zermelo's, restricting which formulas you are allowed to use to define sets rather than restricting which sets can exist. It permits a universal set, the set of all sets, which standard set theory forbids, and nobody could prove it consistent. Not relative to standard set theory, not relative to anything. It sat there, unresolved, for over 70 years, being taught and studied and used, while its status was completely unknown. It got worse in 1954 when Ernst Specker proved that New Foundations refutes the axiom of choice, which nobody had expected, and which the field took as a bad sign. Then in 2010, Randall Holmes announced a proof of consistency. It was long, and it was intricate, and it used a construction called tangled type theory. And the response from the community was not celebration. The response was that the proof was too complicated for anyone to be confident about, and it went unverified for over a decade while Holmes revised it. What settled it, in 2024, was a machine. Skye Wilshaw and collaborators formalized the entire argument in the Lean Proof Assistant, and Lean checked every step, and it holds. New Foundations is consistent relative to standard set theory, 77 years after it was proposed, and the thing that closed the case was not a person. Hold on to that too. It comes back at the end and it does not mean what it looks like it means. Now those are the outright inconsistencies. Alongside them sits a category that is less dramatic and, for my money, more informative about how mathematics actually behaves. Results that were not contradictory but were simply wrong, published, accepted, and built upon. The Italian school of algebraic geometry, active from roughly 1885 to 1935, produced an enormous body of deep and largely correct work under Castelnuovo, Enriquez and Severi. It also produced, particularly toward the end, a body of results that were announced with proofs that do not work and conclusions that are false. David Mumford, who won the Fields Medal partly for rebuilding the subject on solid ground, described the situation as one in which you had to learn, from experience and from talking to people, which of Severi's results could be trusted and which could not. That knowledge was oral. It was not in the papers. The classification of finite simple groups was announced complete in 1983. It is one of the largest collaborative results in the history of mathematics, running to something on the order of 10,000 pages across hundreds of papers by over 100 authors. In the 1990s it emerged that one case, the quasithin groups, had a gap. It was not a small gap. Michael Ashbacher and Stephen Smith published the repair in 2004. It runs to 1,221 pages. For 21 years, the mathematical community believed a theorem was proved that was not proved. Nothing collapsed. The theorem turned out to be true. But the belief and the proof came apart for 2 decades, in the most heavily scrutinized result of its era, and nobody noticed. And then there is the case that sits closest to home, which is Fermat. Andrew Wiles proved Fermat's last theorem in 1995, and the proof as written uses the machinery of Alexander Grothendieck, which is standard equipment across modern algebraic geometry. That machinery is normally set up using what Grothendieck called universes, and the existence of the universes you need is equivalent, over standard set theory, to the existence of inaccessible cardinals, which are exactly the large cardinals we were talking about a moment ago, the ones whose existence cannot be proved and whose consistency cannot be established. Read literally the most celebrated proof in modern number theory of a statement about whole numbers that a schoolchild can understand appeared to depend on an assumption strictly stronger than the standard foundations of mathematics. That is not the current view, and the person who did most to change it is a philosopher and historian of mathematics named Colin McClarty. In a paper in the Bulletin of Symbolic Logic, Volume 16, Issue 3, pages 359 to 377, he showed that Grothendieck's tools can be founded on a system with the strength of finite order arithmetic, which is far weaker than standard set theory and contains no large cardinals at all. Angus MacIntyre has pushed a program aiming to get the arithmetic content down further still, toward Pinot arithmetic. The universes were removable. The alarming reading was wrong. And I want to be precise about why it was wrong, because there is a lesson in the shape of it. It was not wrong because someone checked and found the universes were never used. They were used. It was wrong because someone did a substantial amount of new work, decades later, to show that a different route existed. For 15 years, the strongest result in number theory sat in the literature resting, as written, on an assumption whose consistency is unprovable, and the field carried on as though this were a technicality, which, in fairness, it turned out to be. But nobody knew that at the time. They assumed it, and then eventually somebody went and checked, and this time the assumption held. That is the actual epistemic situation, not a fortress, a working practice held together by the fact that so far, when people have gone back and looked, the load has turned out to be bearable. For about 45 years there was a defence available, and it was the defence Hilbert's successors reached for immediately, and I have some sympathy with it. The defence goes like this. Yes, the Godel sentence is unprovable, but look at it. It is a monstrosity, hand-built for the purpose, asserting its own unprovability, of interest to precisely nobody outside logic. The consistency statement is unprovable too, but consistency is a foundational question, and foundational questions have always been philosophically murky. Meanwhile, the actual body of mathematics, the theorems people care about, the results about primes and surfaces and equations, sits entirely inside the provable region. Incompleteness is a property of the fence, not of the field. That defence died in 1977. Jeff Paris and Leo Harrington published a result in the Handbook of Mathematical Logic, pages 1133 to 1142, concerning a strengthened version of Ramsey's theorem. Ramsey's theorem is ordinary combinatorics. It is the mathematics behind the observation that in any group of 6 people, either 3 of them mutually know each other, or 3 of them are mutual strangers. Paris and Harrington took a strengthened finite version of it, a statement about colouring finite sets that any competent combinatorialist could state and would recognise as a normal question. It is true. Pinot arithmetic cannot prove it. It was the first natural mathematical statement, arising from ordinary mathematical practice rather than from logic. Shown to be true and unprovable in the standard system for arithmetic, there is no self-reference in it. There is no encoding. It is a question about colouring sets. Then it got worse, and it got worse in a way I find genuinely delightful. In 1982, Laurie Kirby and Jeff Paris published a paper in the Bulletin of the London Mathematical Society, Volume 14, pages 285 to 293, about a sequence invented by Reuben Goodstein in 1944. A Goodstein sequence is defined by a completely mechanical procedure. Write a number in a particular recursive base notation. Increase the base by 1 everywhere it appears. Subtract 1. Repeat. That is the whole rule. You could teach it to a bright 12-year-old in 10 minutes. Every Goodstein sequence terminates at 0. Pinot arithmetic cannot prove it. And the numbers involved are where it stops being an abstraction. The Goodstein sequence starting at 4 eventually reaches 0, but it takes roughly 3 times 2 to the power of 402,653,211 steps to get there. That step count, written out in ordinary decimal digits, would be about 120 1 million digits long. To reach 0 from the number 4, Kirby and Paris also produced the Hydra game. You have a tree, you chop off a head. The tree grows back more heads according to a fixed rule, faster and faster. Every strategy wins eventually. Pinot arithmetic cannot prove it. And behind all of these sits Harvey Friedman, who has spent 40 years constructing statements of ordinary finite combinatorics, whose proofs require assumptions vastly stronger than standard set theory. Statements about trees, about graphs, about finite games, where the numbers that appear are so large that the notation for describing them has to be built specially. One of them, from the finite form of Kruskal's tree theorem, generates a value that at its 3rd term already exceeds Graham's number, which was for decades the largest number ever used in a serious mathematical proof. The fence was never the fence. Unprovability is not confined to a strange corner of logic where the self-referential sentences live. It reaches directly into combinatorics, into number theory, into the questions people actually work on. The Godel sentence was the first example anyone found because it was the easiest one to build, not because it was the only kind that exists. There is a whole formal theory now of what a system can and cannot say about its own proofs, and it produces one result so strange that I want to state it carefully. In 1955, Martin L. proved the following. Suppose a system can prove the statement if this sentence is provable, then it is true. Suppose it can prove that about some specific sentence. Then the system can prove the sentence itself. Read it again with the consequence in view. A system asserting the reliability of its own proofs about any particular claim is thereby committed to that claim outright. Trusting yourself, formally, is equivalent to asserting the thing you were considering trusting yourself about. The second incompleteness theorem falls out as the special case where the sentence is a plain contradiction. Robert Solovay proved in 1976 that all of this behaviour is captured by a single small modal logic called provability logic, and that it captures it exactly. Everything Pinot arithmetic can verify about its own provability is a theorem of that little system, and nothing more, which means we have a complete map of a system's self-knowledge. We know precisely how much a formal theory can understand about itself. The answer has been computed, and it is not much, and the boundary is sharp. There is also a version of the whole thing that comes from information theory rather than logic, and it goes further in one specific direction. Gregory Chaitin showed in the 1970s that any consistent formal system has a complexity ceiling. There is a number, roughly corresponding to how much information the axioms contain, above which the system cannot prove that any specific string is complex. It can only ever verify randomness below its own size. Robert Solovay later constructed a case so severe that standard set theory, assuming it is sound about arithmetic, cannot determine even one binary digit of the associated halting probability. I should say that Chaitin's own philosophical reading of this, that mathematics is shot through with randomness, and that incompleteness is therefore everywhere and inevitable, has been criticised sharply by logicians, most notably Panu Raatikainen, on the grounds that the technical result does not carry the interpretive weight placed on it. I mention it because I want you to know where the disputes are rather than presenting a settled front that does not exist. But every one of these results is a theorem about what cannot be done. None of them tells you whether the thing you are standing on is sound, and there are, right now, working mathematicians who think that question is genuinely open in the ordinary sense, and who have said so in public and paid a price for it. Vladimir Voevodsky won the Fields Medal in 2002 for work in algebraic geometry that resolved a conjecture that had stood for 30 years. He was, by any measure anyone uses, one of the most capable mathematicians of his generation. He held a permanent position at the Institute for Advanced Study in Princeton, at the same institution where Gödel had spent his career, in the same set of buildings. In 2010 he gave a talk there titled, "What if current foundations of mathematics are inconsistent?" In it he treated the consistency of Pinot arithmetic as an open problem, not as a philosophical worry, as a mathematical question with an unknown answer, which might be answered either way, and which he thought deserved investigation. In correspondence with Harvey Friedman the following year he put it plainly, writing that he thought the inconsistency of Pinot arithmetic, as well as the inconsistency of standard set theory, were open and very interesting problems in mathematics. The reaction from the logic community was not gentle. Several logicians, including Neil Tennant and Juliet Kennedy, argued publicly that he was underweighting Gentzen and misrepresenting the state of the field, and that a Fields medalist saying this in public did damage. Voevodsky did not retract. He spent the last 7 years of his life building an alternative foundation for mathematics, univalent foundations, designed from the ground up to be machine checkable, on the explicit reasoning that human verification of complex proofs is unreliable, and that he had personally published errors that went undetected for years. He died on the 30th of September 2017 at his home in Princeton, aged 51. He is not the only one. In 2011, Edward Nelson at Princeton announced that he had proved Pinot arithmetic inconsistent. He had been working toward it for years, and he believed it. The announcement went out on a public mailing list. Within a few days, Terence Dow and, independently, Daniel Tausk had located a specific error in the argument. Nelson accepted it and withdrew the claim, and then said something that I think is the most honest sentence any mathematician has produced on this subject. He said the consistency of Pinot arithmetic remained an open problem. Harvey Friedman, who has spent his career mapping exactly how strong the assumptions have to be to prove ordinary statements, has said repeatedly that he takes the possibility of a foundational inconsistency seriously enough to be interested in what it would look like. These are not cranks. They are people who have spent their working lives inside the machinery, who know precisely what Godel proved and precisely what Gentzen proved, and who have concluded that the honest position is uncertainty. The counter-argument is the empirical one, and it is a good argument. Standard set theory has been hammered on by very capable people for over a century without producing a contradiction. The relative consistency results connect it to many other systems. Its models have been studied in enormous detail. That track record is not nothing, but a track record is a track record. Frege had a track record for 9 years. Which brings us to the last escape route, and it is the one that anyone who has followed this story to the end assumes must solve it, because it is the one that sounds like it should. Build a machine that checks the proofs. This exists. It has existed for a while, and in the last decade it has become genuinely serious. Systems called proof assistants, of which the most prominent is Lean, take a mathematical argument and verify it step by step against the axioms, mechanically, with no reliance on human attention or human willingness to believe. The mathematical library built for Lean, called MathLib, now contains well over 100,000 formally verified theorems assembled by a distributed community over the last several years. In December of 2020, Peter Scholze, one of the strongest mathematicians alive, posted a challenge. He had proved a theorem in an area he had recently invented, and he was not confident in it. He said publicly that this was the first time he had felt unsure whether one of his own proofs was correct, and he asked whether anyone could get a machine to check it. The community did. The liquid tensor experiment completed in 2022. The theorem holds. That is a real change in how mathematics is done. It is the tool Vervotsky wanted and did not live to see mature, and it is the thing that finally settled the consistency of new foundations after 77 years, and it does not touch the problem, not by a millimeter, because a proof assistant checks derivations against axioms. That is what it does. That is the only thing it does. It confirms, with total mechanical reliability, that the conclusion follows from the assumptions. What it cannot do, in principle, permanently, for the same reason Gödel gave in 1930, is tell you whether the assumptions are sound. Lean's kernel is itself a formal system. To trust that Lean's verification means anything, you have to trust the type theory Lean implements. To verify that type theory, you would need a stronger system, which you cannot verify. The tooling is better. The flaw is the same distance away. And here is the specific consequence, which I want to state as plainly as I can, because everything in this video has been building toward it and we are close enough now that it should be visible. If there is a contradiction in the foundations of mathematics, the machines will not find it. They are not looking for it. They cannot look for it. A proof assistant that encountered a contradiction would not raise an alarm, because from the inside a contradiction does not look like an error. It looks like a proof. It would verify it, cleanly, quickly, and with the same confidence it applies to everything else, because a contradictory system proves everything, and a checker's job is to confirm that proofs are valid. And in a contradictory system they all are. We have built the most rigorous verification infrastructure in the history of the subject, and if the thing it is verifying against is broken, it will be the last system to notice. Godel himself thought about what all of this meant for a long time, and what he concluded is not what gets attributed to him. On the 26th of December, 1951, he gave the Josiah Willard Gibbs Lecture to the American Mathematical Society. It is the most substantial public statement he ever made about the philosophical content of his own work, and he never published it. it sat in his papers until the third volume of his collected works appeared in 1995, 44 years later. In it he states a disjunction, and he says it is inevitable. Either mathematics is incompletable in this sense, he says, that its evident axioms can never be comprised in a finite rule, that is to say, the human mind, even within the realm of pure mathematics, infinitely surpasses the powers of any finite machine, or else there exist absolutely unsolvable Diophantine problems of the type specified. And then he adds, carefully, that the case in which both terms of the disjunction are true is not excluded. Sit with the structure of that for a moment, because it is doing something more subtle than the popular version. He is not claiming that the human mind exceeds machines. He is claiming that one of two things is true, and refusing to say which. Either minds are not machines, or there are questions about whole numbers, ordinary questions with yes or no answers, that no mind and no machine will ever be able to settle. Not questions that are hard, questions that are absolutely unsolvable, in his phrase, permanently by anything. A Diophantine problem is a question about whether a polynomial equation has whole number solutions, the kind of thing on a school exam with larger numbers. Godel is saying that one live possibility is that some of those questions have answers that nothing in the universe can determine. He privately favoured the first branch. He was a Platonist, and he thought the mind had access to mathematical reality that no formal system could capture, and he drew on Husserl's phenomenology to try to say how. But he never claimed to have proved it, and in the lecture he is scrupulous about the difference, which is more than can be said for the argument that took his name and ran with it. In 1961, the philosopher John Lucas argued that the incompleteness theorems establish, on their own, that human minds cannot be machines. The argument is that a human can see the Godel sentence of any given machine is true, while the machine cannot prove it, so the human is doing something the machine cannot. Roger Penrose revived and extended the argument in two books, in 1989 and 1994, and connected it to quantum processes in the brain. The rebuttal is straightforward, and it has been made by Putnam, by Benacerraf and by Pfefferman, and it holds. You can only see that the Godel sentence is true on the assumption that the system is consistent. That assumption is precisely the thing you cannot establish. A human confronted with a formal system sufficiently complex to model their own reasoning is in exactly the same position as the machine. They can see that the sentence is true if the system is consistent. So can the machine. Neither can discharge the condition. The asymmetry the argument needs does not exist. What the theorem actually says is that nobody, human or otherwise, can vouch for the soundness of a system from inside it. That applies to us. We are inside. Most logicians reject the Lucas-Penrose argument, and have for decades. It keeps coming back because it offers a flattering conclusion, and because the flattering conclusion is the version that circulates, while the technical objection is the version that stays in the journals. Godel would not have made that mistake. He was more careful than the people who invoke him. He was also, by 1951, already beginning to lose the ability to distinguish the argument he could make from the world he was living in. He had arrived in Princeton in 1940 after crossing the Soviet Union by rail with his wife Adele, boarding a ship in Yokohama and travelling on to the East Coast by train, because the Atlantic route was closed and Europe was at war, and he had been declared fit for military service by a state he had no intention of serving. He stayed for 38 years. He and Einstein walked home together most days, and Einstein told Oscar Morgenstern near the end of his life that his own work no longer meant much to him, and that he came to the Institute mainly for the privilege of those walks. In December of 1947, Godel applied for American citizenship. Einstein and Morgenstern went with him to Trenton as witnesses. Morgenstern wrote the whole thing down 24 years later, in 1971, explicitly noting that he was working from memory, and that memorandum is the only account we have. In the weeks before the hearing, Godel had studied the Constitution the way he studied everything, and he had found, in his words as Morgenstern recorded them, some inner contradictions, a route by which the document, followed correctly, permits the legal installation of a dictator. Einstein and Morgenstern spent the drive trying to talk him out of raising it. At the hearing, the examiner asked, conversationally, whether the sort of thing that had happened in Germany could happen in the United States. Godel said that he could show exactly how it could. The examiner, who by all accounts was a decent man having a long day, moved the conversation elsewhere. Citizenship was granted. And nobody wrote down what the contradiction was. That is the whole record. One man's recollection, 2 decades late, of the one occasion on which Kurt Gödel found an inconsistency in a real system, a working system, one that people were living inside. Every subsequent reconstruction of what he meant is speculation by people who were not there. The thing he found is gone. He was not well, and he had not been well for a long time. There had been a breakdown in 1934. There was another in 1936, after Moritz Schlick, the founder of the Vienna Circle, the man who had run the room Godel sat silently in for a decade, was shot dead on the steps of the University of Vienna by a former student. Godel spent time in a sanatorium. He came out. He kept working. The paranoia settled over the decades into a specific shape. He became convinced that he was at risk of being poisoned, and the belief was operational rather than vague. He would not eat food unless Adele had prepared it, and by the end he would not eat it unless she had tasted it first in front of him. That was the arrangement. That was how it worked. The system could not verify its own inputs, so it delegated verification to something outside itself. In the autumn of 1977, Adele was hospitalized for 6 months. The verifier was removed, and there was no procedure inside the system for handling that. He stopped eating. Friends and colleagues at the institute tried to intervene and got nowhere. He entered Princeton Hospital in late December. He died there on the 14th of January, 1978, sitting in a chair weighing 65 pounds. The death certificate gives the cause as malnutrition and inanition caused by personality disturbance. I have read that sentence a lot of times over the last few weeks, and I do not think I have got to the bottom of it yet. The man who proved that no sufficiently strong system can establish its own soundness from within, who showed that consistency has to be certified from outside or not at all, and who demonstrated that a system asserting its own reliability is thereby broken, spent the last months of his life unable to certify from inside his own mind that a plate of food was safe, and starved because the external check he depended on had been taken away. I am not going to tell you that his mathematics caused his illness, or that his illness produced his mathematics. There is no evidence for either, and the people who make that argument are usually selling something. What I will say is that the shape is the same shape, and that he saw it in the axioms decades before it closed on him, and that he was the only person in the 20th century in a position to recognize what was happening to him, and to know that there was no argument available that would help. He is the second person in this story to die of starvation. Gerhard Jensen was the first, in a Prague cell in August of 1945, 33 years earlier, aged 35. The two men who went furthest into the question of what mathematics stands on, the only two who produced anything resembling an answer, both died with nothing in them. Frege abandoned arithmetic and died convinced it should be founded on geometry. Bernays wrote out, in careful detail, the formal proof that the program he had given his working life to could not be completed, and published it under the name of the man who had started it. Hilbert lies in Göttingen under 2 sentences that were false when they were carved. And the question is still open, not open in the sense that we are working on it, open in the sense that it has been formally established that no one can close it, and that the work has therefore stopped, and that everything built since has been built anyway. Here is where we are. There is a page of axioms. Everything humanity knows about number, shape, structure, probability, computation and physical law is downstream of that page. It is in the software that flies the aircraft, and the mathematics that secures the banking system, and the models that tell us what the climate is doing. It is load-bearing on a civilizational scale. And somewhere in the whole numbers, in the same endless sequence that contains 17 and 1,000,000 and the number of atoms in your body, there either is or is not a specific integer that codes a proof of a contradiction from that page. It is one or the other. It has been one or the other since long before there were people to write axioms down. The number does not depend on us, and does not respond to us, and is not waiting for anything. If it is there now, and it was there when Hilbert stood up in Paris. And it was there when Godel sat down in the caf with Carnap, and every theorem anyone has ever proved has been simultaneously true and false the entire time, and no one has noticed, because nobody has yet stumbled into the right region. We cannot look for it. The search is unbounded, and the checking machinery would certify the contradiction as readily as it certifies anything else. We cannot prove it is absent, because the proof would have to come from a system we would then have to check, and the ladder goes up forever with nothing underneath it. There will be no warning. There is no mechanism in the structure capable of producing one. Mathematics has no failure mode that looks like a fault. It has exactly one, and it looks like a proof. And we keep going. Every paper, every theorem, every verified line in every formal library is another floor added to a building that Kurt Gödel proved in the winter of 1930 has no possible foundation and cannot ever be given one. We are not standing on solid ground. We are standing on the fact that so far nothing has fallen.